Hey, this is Trig Functions Part 3. We're going to look at how to graph the sine curve. So we'll start by reviewing the unit circle, graph a sine curve, look at its domain and range, and then talk about applications so we understand why this is useful for us. As we saw in the last video, a unit circle is centered at 0, 0 and has a radius of 1. So if I drew a line from the center of the circle to the outside of the circle, that line would be a length of 1. And I can drop down a vertical here to create a right triangle. This distance is the x value of my coordinate point, and the height is the y value. So I would need to use a little bit of trig. Since this is a right triangle, I'm able to do that. And I can mark this as my theta. So sine of theta is opposite over hypotenuse, so y over 1, and cosine of theta is adjacent over hypotenuse, so that's x over 1. So this tells me that the coordinate point, xy, for any of those points around the outside of my circle, is cosine of theta, sine of theta. We're going to be talking about the sine curve today, so we're interested in the height, the length of the height of those triangles for any theta. We looked in the last video at the first quadrant of the unit circle. So remember, this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And we use the first quadrant as our reference angles because we know that all of those points in the second, third, and fourth quadrants have the same absolute value. We just have to think about whether the sine or cosine would be positive or negative, depending on whether it's above or below the x-axis or to the left or right of the y-axis. So we use these values to evaluate trig expressions, and if you want to brush up on that, make sure you check out Trig Functions Part 2. So here I've got a unit circle lined up with a regular coordinate plane. On my unit circle, the x-axis is representing the length of the base of my right triangles, and the y-axis is representing the height. And since any point on my unit circle has a height or base, depending on what that theta is, what the angle measure is at the center of my circle, my inputs on this graph are going to represent theta, or the central angle in my unit circle, and the outputs on my graph are going to represent the height of my right triangle. Okay, so when theta equals 0, I'm looking at this triangle, which isn't actually a triangle, it's a one-dimensional line. And so the height of that triangle is 0. When theta equals pi over 12 radians, I'm right here. And we've got this slide here. So the height when theta equals pi over 12 was found by just making a horizontal line to the right. At pi over 6, I've got this picture, pi over 4, 2 pi over 3, etc. So we can do this all the way around. And you can see that if my angle measure is out here, this is a theta that is greater than pi. And so this one is lining up horizontally with this one here. Okay, and so it makes sense that the outputs are below the x-axis here, because I'm below the x-axis on my unit circle. And it makes sense that my input is past pi radians, because I've gone more than 180 degrees. Alright, so this is the general shape of my sine curve. So I can fill that in, I can connect those dots, because I know that I've got angle measures in between my 15-degree increments that I've used here. And the next thing we want to do is think about the domain and range of this function. Domain is the set of all inputs that map to an output. And in this case, our inputs are theta values. So we want to think about what are all of the possible angle measures that give us a triangle with some height. And so in this case, I can actually have an input, an angle measure, anywhere between negative infinity and infinity. So if I'm at this point here, that's 0 degrees, and I can go past 0 degrees or 0 radians, and I can even go past 2 pi radians or 360 degrees. I can just keep going around and around and around, so theta gets bigger and bigger and bigger, and this pattern repeats over and over again. I can even have a negative theta value if I start at 0 radians and rotate clockwise instead of counterclockwise. So that will fill in this part of my pattern on the graph. So my domain is all real numbers, and my range is from -1 to +1, because that's the minimum height of my triangle and the maximum height of my triangle. We can make one last connection between the unit circle and the graph by looking at the 4 quadrants. So we see that quadrant 1 is between 0 radians and pi/2 radians. So that's going to be this part of my curve here. Quadrant 2 is between pi/2 and pi, so that's this part right here. Quadrant 2, quadrant 1. And we see that this makes sense because as I go from 0 radians to pi/2, the height of my triangle is starting at 0 and getting bigger. Right? It's going to max out at 1, and then as it enters quadrant 2, it's going to start at 1 and go back down to 0. Quadrant 3, which is between pi radians and 3 pi/2, is here. And then quadrant 4 is from 3 pi/2 to pi radians. So we see the connections between the height of the triangle and the angle measure by looking at the quadrants also. One example of a situation that can be modeled by a sine curve, where the inputs are not angle measures and the outputs are not heights of triangles in the unit circle, is the average daily temperature in western Massachusetts. Our x-axis is representing number of days past May 15th, 2016, and our y-axis is representing average daily temperature in degrees Fahrenheit. So we can see that at about 365 days, we've gone through a full cycle. So our temperature has increased and reached its maximum, average maximum, gone back down, hit that 50-degree mark again, decreased as we went into winter, and then started warming back up as we made it towards May 15, 2017. So this is an example of a sine curve being used to model something that happens in the world. Make sure that you check out the next couple of videos, do the practice problems, and let me know when you're ready for a retake.